Hi, I'm Dan Burns with PASCO Scientific, and we're really excited about Roller Coaster Day. We're going to be taking our PASCO Scientific sensors to Six Flags in Vallejo and... What? Oh, that's right. We're not going to be taking them to Six Flags in Vallejo, but we're going to use our imagination to think about what it would be like going over the first big hill on what you'll find on most roller coasters. And so to help us see what that would be like, I have our PASCO wireless acceleration altimeter. And it will measure the acceleration in this direction. It's a 3-axis accelerometer. We'll be looking at the acceleration in this direction, and up is positive. And I have it set so when it's just sitting here, the acceleration is 0. And it also has the altimeter on it, which would measure the height of that big hill on the roller coaster and height of any loops, etc. as you go around. Here in the studio, it's just going to measure small changes in height, so it doesn't work quite as well as it would there, but you'll get to see how it does work. And so let's imagine what it's like on that first big hill. First, you're click, 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 going up the roller coaster hill very slowly. Very slowly. And then you get to the top and you're starting to go over, you're starting to get kind of nervous seeing how high you are. And then you're almost in free fall as you drop, and then at the bottom, stop your vertical motion anyway. And so we can see what that looked like on the computer. That drop is this negative acceleration here. It's about 1 g, 9.8 meters per second. And then there was a large force stopping it at the bottom, and that you also feel on the roller coaster. Now, this is pretty exciting, sometimes a little scary, but you also feel weird on this big hill as you go down and then when you get to the bottom. And there's a reason you feel weird that you may not be aware of. And so let's take a look at why that is. It's because inside of you, you have a bunch of internal organs. Now, I'm a physics teacher, not a biology teacher, so I'm not going to name them for you. So it's your guts, right? And they're hanging on these elastic membranes in your chest cavity. And when you first go over that hill, they actually move. And so when you start to fall down that big hill almost in free fall, your organs actually move up. And you can sort of feel that. It feels weird. If you just ate a big funnel cake or something, it feels like it's going to make its way back out. But before it has a chance to, you hit the bottom, and they actually go down then, and then eventually settle back where they belong. And so that motion of your internal organs makes you feel weird. And so I created a little model of that. And so this blue case is your chest cavity, and then here's your internal organs hanging from membranes. Now I also have some rubber bands in the bottom there just to keep it from flapping out there, but mainly just think of it hanging from these rubber bands. And so watch carefully what happens when I let go. Watch where the guts move relative to the blue box, your chest cavity. You see that? It happens pretty quick. So I'll do it again. What you should be seeing is this moving up inside the case right when I let go. And then when I catch it again, that's like hitting the bottom of the hill, you'll hear it bang onto the box. Now your organs don't bang, but they do kind of hang down lower there. Now let's take a look at what this looks like in slow-mo. Well, let's talk a little bit about why your internal organs move relative to your chest cavity when you go over that first big hill and go into near free fall, and then again when you hit the bottom, why they move down relative to your chest cavity. Obviously, your whole body is moving down. It's the relative motion we're talking about. So I have a free body diagram of your internal organs. And so the FG represents the pull of gravity on them, and that's down. And I've sort of simplified the upward force on it as just being a tension force from the membranes that they're hanging from. There's also some support forces as they rest on each other and at the bottom, but we're focusing on this tension. And that is due to the membranes being stretched in your abdominal cavity, kind of like a rubber band. Now, when you go over the hill and you go into free fall, this tension goes away. And so without that tension, all you have is the downward pull of gravity, and you accelerate down with the roller coaster and everything else. But when that tension goes away, remember those membranes were stretched like a rubber band, they go back to their original length. And so to stretch a rubber band, you need to pull from both sides. I can't stretch it just pulling from one side. And so this represents the membranes before you go into that drop over the hill. And when you go over the top of your cavity is not pulling up anymore. So the rubber band goes back to its original length. Those membranes go back to their original length. And so these organs shift up in your chest cavity. And then when you hit bottom, now your internal organs stretch downward because the acceleration now is up. And so you need a large upward force greater than the weight to cause that. And so it stretches even more, and that tension force gets more. But don't worry, the roller coaster engineers know what they're doing. You're not injured by any of this. Hopefully you have fun doing it. And I can't wait to ride a roller coaster again. I hope you'll be riding them again soon too.